This conference will now be recorded.
Hello, everybody. Jordan Garth here with the Satellite Book Club Seminar Series on location in Minneapolis, Minnesota for session number 169. It's a beautiful, sunny fall day here. A little wind front coming through in a few hours. Glad to have this presentation on the NESDIS Enterprise Rainfall Rate QPE product with Dr. Bob Kuligowski from NESDIS-STAR. We're here with Sean Deviney, Senior Meteorologist from the North Central River Forecast Center, who's going to facilitate the discussion following Bob's presentation. Just a few reminders, as you heard, this session is being recorded. There's an opportunity for Q&A after the presentation. Please post your questions in the chat. We'll field them in the order they're asked. If you've not signed in with your full name, perhaps you're using an office account, please note your name when asking a question in the chat so we can follow up if necessary. We're also looking for future presenters for the Satellite Book Club. If you would like to present, please talk to Kashad Bowman and Emily Maddox, who are here with me in the room today. The training team can help create training materials that may be unavailable or you may be unaware of. Ross Van Til can help with that. I'd like to thank our Tower S team, particularly Kashad and Emily. Give a wave. The Office of the Chief Learning Officer, the GOSAR, JPSS programs, all of you for being with us, our presenter, and last but not least, our facilitator, Sean. Without further ado, let's dive into today's presentation with Dr. Bob Kuligowski, who's been with NESDIS-STAR for nearly 25 years and was actually an operational forecaster 30 years ago. I'm sure things haven't changed at all. Today, he focuses on retrieving rainfall from satellites for use in short-term forecasting. Bob, welcome to the Satellite Book Club.
Thanks, Jordan. And yes, I'll just say paper. Lots and lots and lots of paper. Maps hanging on walls, everything. It was a totally different era. Anyway, I'm not here to revisit the old days. I'm here to talk about the NESDIS Enterprise Rainfall Rate QPE product. So what I'd like to do is start off, hang on. There we go. So I want to give a little bit of context in what I call the trade-off between accuracy and latency. And once I get into that, I think everybody in this room is going to know exactly what I mean. I'll briefly describe the NESDIS Enterprise Rainfall Rate algorithm and talk about how it's different from the baseline version. I promise there are no equations in this talk. And then I'll give a couple of examples. I'll walk us through 3 different case studies. Won't go too deep into it just because in the interest of time, but hopefully they'll give you a flavor for the algorithm's performance in different situations. So let's start with the accuracy latency trade-off. So the key is that the longer you wait, the more information that you have. That's true in weather forecasting, that's true in a lot of things. The problem is at some point you have to make a decision. And so there are very real limits as to how long you can wait, even though past your deadline, you're going to have more information that will be helpful. That's true in forecasting and in life in general. And precip is one of many classic examples of that, because you think of the radar world, and you look at a radar-only product, depending where you are, it gives you decent to good results, and it's very, very quick. If you've got time to wait for gauges to be brought in, you get a better product, you get something more refined. And then if you've got a lot of time and you can wait for daily gauges, which are an order of magnitude more common, you get even better results. So one thing to keep in mind with all is that what you're going to be able to use is going to depend on your application. If you're doing short fuse flash flood forecasting, your deadlines are going to be very different than if you're doing something, say, for water resources management, crop forecasting, reservoir management, so on. So one example, this is from MRMS, is just how you can get refinement just going from a radar-only product on the left to a the gauge-adjusted MRMS on the right. This is a 6-hour total from a flash flood case in Idaho Falls, Idaho, that I'll be talking to a little later on. The differences between the two aren't drastic, which is good. That gives us some confidence in the radar-only product, but we do see that in this case, relative to the gauges, the radar was more aggressive, and that bringing in the gauge data did reduce that somewhat and refine the details a little bit more of what was going on. And this, again, is just, it's not meant to be a critique. This is meant just to illustrate the notion that how long you can afford to wait is going to have some impact on the quality of the product that is going to be available to you. And it's true for satellites as well. And basically the trade-off we have to deal with here is that Geostationary infrared data comes in very quickly. You've got a satellite that's got a constant line of sight with the Earth, and you're able to bring data down very, very quickly. You're able to do a very rapid refresh, whereas with LEO microwave, you're in low Earth orbit, but you don't, since you're not staring at a particular location, you're only getting a certain number of overpasses a day. You don't get the same quantity of data, but the quality is higher because microwave rain rates are sensitive to the contents of the entire 3D structure of the cloud, not just to the cloud top, which is what you're basically seeing in the GeoIR. So it's just a cartoon. This is not anything quantitative, but I've just made a little plot where the timeliness is going to be on the x-axis. So the farther right you go, the longer you got to wait, and the accuracy is on the y-axis. The higher you go, the more accurate you get. So your geostationary data, again, that shows up very, very quickly. It's a matter of minutes between when the picture gets taken and when we've got it on Earth. Low orbiting Earth data takes longer. Now, if you have direct broadcast for your particular area, yes, we can close this gap down to something on the order of what we get for geostationary. But in general, you're talking about a delay of a few hours to get the data. And then, of course, gauge data all depends. There's some, there's some gauges that have really good telemetry where you can get that data in under an hour. There's some things like co-ops, and CocoRAs, where obviously you've got to wait until someone takes a physical measurement. And for satellite, the different satellite estimates of precipitation that live in this continuum. The NESDIS Enterprise rain rate is going to be in the lower left part of our plot. There's a very small delay, but because the only information we've really got to work with is the geostationary infrared, we're going to have a relatively lower information content. When you look at algorithms like CMORPH2 and iMerge that are able to use the microwave data directly, that enhances their accuracy. But again, it takes time to get those data. Typically 4 hours from iMerge early, 14 hours for iMerge late, and then there's a number of implements. That's not the word I want. A number of versions of CMORPH2 that come out as additional information comes in. Now, again, this is not meant to say iMerge is 5 times or 6 times as accurate as the enterprise rain rate. This is just a cartoon just to illustrate this concept that there's a big trade-off here. If you want something fast, you're going to have to sacrifice some quality because you're just not going to have the ingredients to put in the pot that you would if you waited. So the enterprise rain rate algorithm, obviously we're looking for a low latency first look satellite-based rain estimate to supplement radar engages. That's our goal. It's an infrared-based algorithm because, again, we want to have something timely, so with something we can produce within a few minutes after the data become available on the ground. But we calibrate it against microwave rain rates in order to try to capture at least some of the higher information content of those microwave-derived rain rates. And that calibration gets updated in real time, so we're able to capture seasonal changes, for instance, differences in the proportion of convective to stratiform precipitation, so on. We also have spatial variations in the calibration because, again, there are spatial variations in the types of precipitation, cloud particle size, other things that will affect the relationship between the infrared-based cloud top properties and the surface rainfall rates. This enterprise algorithm is going to replace the baseline soon. The operational date is still, at this point, want to say TBD. I'm hoping by early next year. But we're still waiting on, there's basically just some things that need to be done as far as the actual implementation to make that happen. But we are going to have the operational readiness review soon. So how is this different from the baseline version, especially for those of you who've experienced the baseline version in AWIPS? One is that the baseline version had to have the time varying calibration taken out. It had to have a fixed calibration, and the parallax calibration were removed from the baseline. These were decisions that were made for non-scientific reasons. I didn't agree with them, but we'll just leave it at that. So we brought those back in. We also shrunk the calibration regions down because we found we had a more precise calibration when we did that. This is another engineering thing because if the calibration region is smaller in space, you've got to take more time to accumulate enough calibration data to do the calibration. So that's another of those engineering trade-offs. We also added an adjustment for subcloud evaporation. We had a lot of issues with the old algorithm of overestimating precip or giving false alarms in drier air, particularly out west. So we used the mean layer relative humidity from the GFS to do that. And this is something that was taken from the global hydroestimator algorithm. And of course, there's other bits of fine tuning that are here and there because I'm a scientist and I can't resist tinkering, but I won't get into all of that. So I promise this is the only other graphic you're going to see that's not going to have a map background. So when I'm looking at scatter plots for rainfall are not very helpful to look at because you get these big black clouds of points and you can't tell what's going on. So I prefer to do frequency plots. So the x-axis is the MRMS rain rate, and ranged here from 0 to 50 millimeters an hour. The y-axis is going to be the baseline algorithm on the left, the enterprise algorithm on the right. The colors are just colors representing the frequency of the points. So warm colors are more frequent values, cool colors are less frequent values. And as you would expect, precip is very, very strong, and it's a logarithmic scale. So precip is very, very strongly skewed toward light rain rates and away from heavier rain rates, as you'd expect. Now, if the precip algorithms were perfect, all of the points would be right along this one-to-one line. You would have no errors. Every MRMS, every satellite value and every MRMS value would match perfectly. Obviously, that's not the case. And so what we're trying to do is figure out, okay, what are, there's a lot of scatter, and there's a question at this point of, okay, how do we, this is a way of getting at least a bird's eye view of what are the impacts from a new algorithm. So, and then, sorry, this is the one-to-one line, and then the dashed line here is the best fit, is a linear best fit line. So a couple takeaways we can take from this. One is that, if we have a point that's right along the y-axis, so the MRMS value is 0, and the satellite value is something bigger than 0, that's a false alarm. That's something we don't want. And one of the good things with the Enterprise is that we reduce the false alarm rainfall by about 2/3 in terms of volume, and this is largely because of the addition of the GFS humidity information in order to get rid of precip and dry air. Another piece of good news is that we have also reduced the amount of missed rainfall. So again, if you have points that are along the 0 value for the satellite, so satellite has nothing, but the MRMS has something more than nothing, means it's missed rainfall. The MRMS had rainfall, the satellite missed it. And we see here that we got about, and you can't tell it's just by reading the plot, I did the numbers elsewhere, but about a reduction of about 1/8 of missed rainfall. So it's not just, so we didn't just dry everything out and reduce false alarm rainfall. That way we did skillfully, and we also reduced the amount of rainfall that we missed. But the news isn't all good, because we did reduce some heavier rain that was actually real. We see that a lot of this part of the plot has gotten pushed to the right, or to the left rather, which is not preferable. So that's a price you paid. It's hard to make, it's like with NWP, it's hard to make a change that is going to make everything universally better. There are trade-offs, and so part of this is trying to figure out what the relative merits of the stuff on each side of the trade-off and what to do. All right, last of that, everything else has maps in it. So I'm going to present 3 examples. The first is going to be the flash floods in Dallas, Texas, from late August 2022. So we had 2 deaths and about $850 million in damages. Dallas-Fort Worth Airport broke a bunch of rainfall records. I think 3.01 inches an hour. They broke their daily. They came darn close to breaking their monthly. And what Weather Prediction Center was on it. They issued a couple of mesoscale precipitation discussions on it. And you can see just by looking at the plots that this is a situation where you have a quasi-stationary frontal boundary to the south of Dallas-Fort Worth Metroplex. You've got a really strong inflow of moist air coming from the south, and then you've got some height falls on top of it. Great recipe for training thunderstorms, and that's exactly what we saw. So let's take a look first at some loops. There's a 48-hour loop, and I'll explain why it's 48 hours since the event didn't last that long. But the Dallas-Fort Worth Metroplex is the white circle, just to make it a little bit easier to see. The gauge-adjusted MRMS is on the left, so I'm looking at ground truthing it, and then the baseline is on the right. So we see, first of all, I'll get back to the start of the loop. Early in the event, we see the training thunderstorm starting to appear over the Metroplex. We see it, the baseline algorithm captures it, but it also has a whole bunch of excitement that isn't really there. And then you get this big hairy thing that goes heading for Del Rio and the lower Rio Grande River, which is obviously fictitious. The other challenge we have is that the baseline algorithm actually underestimated a lot of the later thunderstorms that went through Louisiana and into Mississippi. When we look at the Enterprise instead, we see the Enterprise starting to capture the training thunderstorms over Dallas. See it right in here without that huge blow up that you had before. So it reduced the overestimation of heavy precipitation. It also didn't have nearly as much of an Armageddon-esque situation heading for the lower Rio Grande Valley. However, it did still underestimate precipitation over Louisiana. Let's take one more look. So we see the training thunderstorms right. There we go. So we've captured pretty well without all the huge overblown. Again, this thing is a lot less nasty and wrong than it was in the first go around. So if we look at the totals, 48-hour totals, over the Dallas Metroplex, the baseline actually overdid it a little bit, but the Enterprise came out pretty well compared to, over the Dallas-Fort Worth metro area. You end up having maximum precip amounts on the order of about 300 millimeters, which is what the ground truth indicated. So from the perspective, if I just did a close-up of the Dallas Metroplex, I'd say this was, we had a big win. But there's some other things we want to look at, because again, there was this huge false alarm over southwestern Texas, which obviously wasn't indicated by the MRMS data. And we found the Enterprise algorithm still overplayed it, but didn't overplay it nearly as bad as the baseline did. But we also see the part we have improvements to be made, because over northern Louisiana, the precip amounts in MRMS were actually on par with what we saw in the Dallas-Fort Worth Metroplex. You just had much lower population density. And that the baseline and Enterprise both underdid it, and the Enterprise underdid it even more. So this is the Dallas case. This was a win. The other cases, it's a bit more of a mixed bag. The second case I want to look at is September 2023 New York City flash floods, where we had a low offshore that sucked up the remains of Ophelia and basically pushed it against a frontal boundary that was just off the coastline. We had some height falls to add some stability, so we had some decent ML values. Well, not really decent, but a little tongue to the west of it. But the point is that this was, again, something WPC was on top of it, and we knew this was going to be a significant event. Ended up causing $100 million in damage. Thankfully, no fatalities I'm aware of, but it affected, every single, the entire, there were delays along the entire New York subway system. I should say every single line had delays because of flooded stations, so on and so forth. This was definitely a headline grabber. So how did we do? Let's look at the baseline first, and we see one thing off the bat is that it's having a hard time capturing those first couple bands that moved in. By the time you get to the third band of precip, we're starting to get an idea of what's going on. The difficulty is that it's doing a pretty good job of pinpointing the areas where the most intense precip is, but we're not capturing these regions where you have these 2 to 3 inch an hour, 50 millimeter an hour higher rain rates that are embedded in these areas of convection, that they're being underdone by the baseline, by the baseline algorithm, and that's obviously not good. So it's pointing the finger, but it's not. Rain rates of half an inch an hour where it's maxing out on, that's not something to get excited about. How did the Enterprise do? The Enterprise did better. We have, it did a better job of capturing that initial band, which then fell apart, captures the second band, does a better job overall, but again, we're still having a magnitude problem. And we've got a longer duration of the heavier precip, so we see the totals look better, but we're still not capturing those mesoscale details. One of the challenges with IR satellite in general is that you end up with a lot of anvils that will obscure the details underneath, and so what can happen is you can end up smushing out or flattening the heaviest precipitation in instances like this, where you've got these really small areas of very intense rainfall. So let's look at the totals. The MRMS is on the left, and you see a very large isohyet of over 100 millimeters of precipitation. The Enterprise at least had, was a little more on track than the baseline. The baseline significantly underestimated this event, especially over Massachusetts. The Enterprise in this case did better, which again is good, considering that again we've got an algorithm that's having, that we said we did lose some skill in some instances for heavier precip because of that, but we still have underestimated. It still comes out to be a significant event, but it's but instead of having this huge isohyet of 4 inches or more, we end up with one that's only covering basically western Long Island, and then the what's basically a 4-inch isohyet in the MRMS ends up being probably about a 2 to 3 inch isohyet for the satellite. So so this is one where it did at least, the accumulations captured the notion of a significant event, but didn't capture the full brunt of it. But again, the Enterprise did represent a significant improvement over the baseline. Last one we're going to talk about is the Idaho Falls flash flood in May of 2023, which caused about $1 million in damage, mostly in Idaho Falls and Rexburg. And all of you are probably thinking, Rexburg, that sounds familiar. Yes, that's because that is the town that sadly was flooded when the Grand Teton Dam failed in June of 1975, which I'm sure you all remember, or June of 76, which at least a flood geek like me remembers that. Anyway, point is, quasi-stationary boundary. You've got, again, vortex coming in. You've got height falls. There's not humongous amounts of moisture to work with like we had in those previous two cases, but you still get the potential for getting short periods of very intense rainfall. So this is a much smaller scale event in a mountainous region. So what this question we want to do is, how do we do here, where we've got something that's not this great big organized convective, MCS type thing like we had in the other in the Dallas situation, for instance. And what we find is, again, this was a challenging one. The MRMS is on the left. This is a 1 hour loop. I did 1 hour loops just so I could show the gauge adjusted stuff. And we do see, we don't have training thunderstorms in this case, but you do see an axis along, along north of the frontal boundary along which we're getting thunderstorm formation, but they are, in this case, moving pretty rapidly to the northeast. We see the baseline QPE, which again at least points out the idea is there, but it doesn't capture the intensity. Again, part of it being that the broader area of cold cloud tops means the algorithm is going to tend to smear these things out rather than capture the really fine scale details. So one of the disadvantages in IR, again, is you can't see what's happening underneath the cloud top, and there's a lot of interesting critical stuff that goes on there. Take a quick look at the Enterprise. And the Enterprise, again, we get the idea that it points to it. It does a good job as far as capturing the location of the heaviest precipitation, and the max is just a smidge higher, but it doesn't really, again, the max even for the Enterprise is somewhere between 1/4 and 1/2 inch of rain in an hour, whereas we had, final, results on the ground were 1.5 to 2 inches, possibly some 3 inch in an hour reports in Idaho Falls. So looking at the totals, again, this one where MRMS, you see this is I showed before. You see this the area, you see the area of significant ISO heights of 1 to 2 inches of precipitation, including in the Idaho Falls area, Rexburg area, which is just to the northwest. The Enterprise at least pointed to the idea you're going to get a more significant precip event in the Idaho Falls Rexburg area, but again underestimated. It has less than 1 inch. The baseline in some areas actually did better. In the areas south of the reservoir, and I forget the Snake River, I'll forget the name. There's a reservoir in the Snake River, I forget the name of it, but the southwest, it actually did a better job at capturing that, and did about this, ended up doing about the same in Idaho Falls and a little bit less north of Rexburg. But again, this is one of the situations where if you're trying to use IR data, I mean, you've seen it all when you've looked at thunderstorms in radar. You get these huge, the areas of cold cloud tops are much larger than the area of precipitation underneath them at any given time, and that's part of what makes this so challenging. So let me summarize. So again, the NESDIS Rainfall Rate RQP algorithm product is meant to be a low latency, within a matter of minutes, first look satellite-based rainfall estimate. It is obviously does not have the same skill level as radar and gauges. It's meant to supplement them, especially in regions where you don't have radar or where you conveniently have, say, radar out for maintenance at the time when something of interest is happening. And in order to achieve this timeliness, this low latency, we do the retrieval straight from infrared rain rates. We only use the microwave rain rates as an offline calibration standard. We've got about a 12-hour delay in which that's done. So again, if you can wait a few hours for a particular application, CMOR 2 or iMerge directly use the microwave rain rates, and they're generally going to be more accurate as a result of that. The emphasis here is on low latency, first look, type of situations. And then we saw that overall, the Enterprise version does miss less rainfall, and it has fewer false alarms than the baseline does, but it still often underdoes heavy rainfall, and we're continuing to work on that through doing case studies like these. And again, it can be challenging. Last fall, I thought I had a solution that was, that looked absolutely wonderful when I did a study on Hurricane Ida in the Mid-Atlantic states. The results improved dramatically. Then I ran it for the entire month of January, the entire month of July, and evaluated results for the entire CONUS and found that, yeah, the good news is it did a lot better for heavy precip. The bad news is it started grossly overestimating light to moderate precipitation, and that wasn't a trade-off I was happy with. So that's where we are. So if we have any questions, I can take them now.
Okay, all right, thank you, Bob, for the presentation, and I want to just encourage everyone to please stay on for the discussion if you can. It's just a reminder to go ahead and you can send in your questions into the chat, and we will go through those in the order that they came in. We particularly would love to hear from some of the field offices out there, regional headquarters as well, and then again, just to please include your name when you are asking a question. That would be great. So I want to go ahead and just before we dive into it, I want to remind folks that 2 weeks from today, on Thursday, November 30th, we will have the next Satellite Book Club series at noon Eastern Time, and that will be with Kevin Thiel from the SBC Satellite Liaison, and he'll discuss a research operations perspective of the geostationary lightning mapper. So please put that on your calendar and join us for that. I also want to go ahead and encourage people to contact the Towers team, Kashad Bowman and Emily Maddox in particular, for questions about the Satellite Book Club series and for configuration of satellite products. All right, so at this time, we can go ahead and get into the discussion and the questions with Bob here. Once again, just go ahead and submit those in the chat and we'll go through those. I already see a couple that have come in, so thanks for sending those in. We'll go ahead here, Bob, and start. The first question we got was from Nicholas Spenner, and here's the question. Along the lines of, along the lines of how the probs of MBFR and etc. products work with the RAP model data, is there any way that probability matching of the cold cloud top satellite data and model data could assign higher rates where an anvil is obscuring thunderstorm details?
So I guess, Nicholas, you're talking about using the RAP as, I guess I'd have to evaluate just how well the RAP is doing as far as indicating the location of the heavy precipitation. Because one of the challenges I've had when looking at least at I haven't looked as much as looking at the HER, is that there tends to, if you look at a forecast for a given time with different leads, there tends to be a lot of jumping around as to where the convection is occurring. So that'd be one concern I have, at least for using model data in that way. Now, as far as the probability matching, though, you raise an excellent point that one of the challenges we have, and it really occurs with any learning method, is that depending on the kind of what they call a loss function, basically the penalty function for that you're trying to minimize to reduce error, that one of the challenges of precip of it being so skewed toward light rain rates is that typically machine learning algorithms, including just simple regression, are going to reward you for getting the light precip perfectly, and aren't going to care if you get the heavy precip wrong, because there are just so few data points with heavy precip that it doesn't contribute much to the error. Now, the way that I've gotten around this is that actually one of the steps in the algorithm, I didn't want to get too deep into the details, is where I actually then take the original retrievals that the rainfall algorithm does, and I match them back up. I do a probability matching against the microwave rain rates in order to force the distribution to look like the distribution of the microwave rain rates. Even though I do that, it reduces the dry bias but doesn't get rid of it. And one of the great mysteries of the last few years is why that is. And I have tried all kinds of things and looked all over the place, in the code to try to figure out, is there a bug somewhere? Why is it that the distribution of the rain rates perfectly matches the microwave for when it's run on the training data set, but when you run it on independent data, all of a sudden you get this incredible, all of a sudden you still get a dry bias. And I don't know the answer to that. I'm still trying to work with that. Still trying to figure out if there's something else that I'm missing here in terms of either some previously unbeknown code bug, or if there's just some reason because of the nature of mathematics that is causing the problem. But yeah, definitely trying to figure out ways to address that. Like I said, it definitely helped. If I showed you the results without that probability matching, it would have been really depressing. So it's made an impact. It just has not gotten us across the finish line in that regard.
All right, thank you, Bob. And Nicholas did chat back that he appreciates it, and then you answered his question to exactly what he was wondering. So
Okay.
thank you for that. The next question is from Dan Lindsay. He says, thanks, Bob, for the presentation. Can you say a few words about some possible future rain estimation algorithms, including those that use machine learning?
Yep. Thanks, Dan. I have not mentioned. I didn't miss. I've got the chat up too, so you didn't miss mention of it. I wanted to focus more on where we were right now, just in the interest of time. There's a couple of AIML algorithms. One been developed at the University of Oklahoma, another one at Colorado State, and I've got somebody now who's working with me to basically evaluate those. We want to find what's the best parts of both of them, and can we come up with some kind of a combination that gives even more improvement. One of the issues, even with AIML, that we run into again is trying to make sure that the heavy precip events that we're interested in get enough representation in the data set so that the algorithm is going to have the guts to actually do daring things and not just play it really conservative because there's not much penalty. One of the consequences of that in the evaluation we've done of the algorithm that came out of the University of Oklahoma is that they do overestimate precip in general, and especially light precipitation. So we're trying to work with that. But we've got a time frame for a couple of years to just do basically do the comparison, find the best parts of both algorithms, see if there are other things we want to do to improve as well, and then go for there. So it is on the horizon, because we can certainly capture much more information with AIML. There's no question about it. It's just trying to make sure that we capture things that are physically reasonable and not capture things that are particular to whatever data set we happen to be feeding it.
All right, thanks, Bob. And thanks for the questions that keep coming in. We still have about 10 minutes before we're going to wrap it up, so keep them coming if you have them. We'll get to the next one here. This is from Dan Berkowitz at the Radar Operations Center, and he asks, has any study been done to evaluate cold top satellite QPE versus warm top satellite QPE?
Good question. We haven't done one. Back in the days of the hydro estimator, we knew that we did a lot better for cold top than warm top. There was a tendency to underestimate warm top. I suspect the same is the case here. I have not, and I've kind of seen it just by eyeballing situations like the ones that looking at case studies. I haven't done a comprehensive validation. I've got a way that I know of to do it, and now that I think about it, I know exactly the person who's working with me who I can ask to help me with that. Because I think that would be, we're basically do a validation as a function of the IR brightness temperature and get a better handle on what the bias structure looks like for that. So thank you for the reminder. That is something I just added that to my to-do list.
All right. Thanks, Bob. We'll keep on rolling. The next question is from Satya Kaluri. And the question is, how does the enterprise algorithm differ from CMORPH in terms of accuracy?
Okay. It is not as accurate as CMORPH. In one sense, you can't expect it to be, because it doesn't. CMORPH uses the microwave data directly, whereas I'm using it indirectly as a calibration data source. And this is, again, that trade-off that I talked about at the beginning of timeliness versus accuracy. My goal is to have something that's a very quick first look that gives you information of a starting point within a few minutes, even if you don't have time to wait for the additional microwave information that's going to, and even gauge information that's going to get you a better result. So CMORPH is more accurate in general. Again, in a certain sense, I'm not competing with CMORPH because it's a different lead time for CMORPH. I mean, I know they're trying to reduce the lead time of CMORPH by using extrapolation only rather than doing interpolation between two microwave overpasses. That does significantly degrade the accuracy. It's kind of similar to the difference between the early and late iMerge. But I haven't done a quantitative evaluation of it. Then again, because I see myself in CMORPH as partly swimming in different lanes.
Got it. Thanks, Bob. All right, this next one is from Mike Stavish, and I'll second this question. This one I've been thinking about myself. Can you comment on performance in stratiform events, perhaps AR events in the West as well?
Stratiform is hard, because you've got very shallow clouds, which the algorithm, and the enterprise does a much better job with stratiform than the baseline was. but it's going to be challenging. Stratform is really very hard just because the clouds are so stinking warm. Atmospheric river events, I'll talk about those. Those are challenging from a different perspective because of atmospheric events in the west. What makes those extraordinary is the interaction with topography. That it's not just that you've got this hose of PW trained on a region, but that hose is impinging upon terrain that's going to force uplift and so on and so forth. And the enterprise rain rate algorithm does not have an orographic precipitation adjustment. The hydro estimator has one. The problem I've always had with it is that it puts the enhancements and the reductions in the wrong places. And that's one of those things where, yeah, it gives a heads up there's going to be that there's going to be orographic modulation. But I also don't want to put out a product that gives a wildly misleading idea of where that stuff is. That orographic modulation of precipitation is a whole lot more complicated than just air flows up, air flows down. Air can flow around. Stability will determine whether it flows up or down or goes around. There are a whole bunch of other considerations that aren't captured by a lot of these really simple, take your orography and take your wind vector and just put, and put the two together and voila. It looks good when you look at a map, but when you try actually validating against gauges, you end up with results that are very disappointing. The one thing I will say is if you have instances where convective uplift releases potential instability, those will show up because you're going to get very cold cloud signatures on top of it. But cedar feeder isn't, because the orographic cap cloud that's causing all the enhancement is invisible. We can kind of infer that, okay, conditions are probably favorable because of certain stability and moisture considerations, but you can't actually observe the thing from the satellite. You can't see in the IR because, of course, there's optically thick rain clouds on top of it, and you can't see it in the microwave because those clouds are often, largely water clouds, and so you're not going to get the ice scattering that's going to make it show up in the microwave. So this is one of those areas where you're going to have to use other information in order to do it. And some of the work that's been done at Colorado State University is trying to capture some of these orographic using a neural network approach. It's looked promising. So this is one of the pieces from their approach that we want to consider in this algorithm and see, is this something where we can use neural nets and the appropriate information to better capture orography. And if we do that, if we're able to do that, I think we'll see a dramatic improvement in performance for these atmospheric rivers out in the West Coast.
Got it. Thank you, Bob. Does anybody else have any questions, either in the chat or here in the room? Go ahead and ask.
Okay. I see your question, Sheldon. We do not do an EL adjustment for increasing rain rates. I mean, at this point, it would be an EL adjustment where we'd alter the brightness temperature and calibrate against that. We tried it once and we really didn't get satisfactory results with it. I'm certainly willing to take another try now that I've got somebody to kind of help me with some of those things. So I'm making a note to myself to revisit it just in case. The idea behind it, just to help everybody else, is that when in the hydro estimator, when the convective equilibrium level was really warm, in this case warmer than 200, then you just are not going to get really cold cloud tops because the atmosphere is not going to let you do it. You're going to slam into, you're going to hit the ceiling of your area of positive buoyancy at a very low, relatively low level, but you can get some tremendous updrafts underneath it. But the question is whether we can, and the equilibrium level adjustment is very helpful with the hydro estimator. So the initial efforts we made to try to do this in the enterprise rain rate algorithm weren't very promising, but now that I've got someone else to help me out in this, I'm very happy to take a fresh look at that. So thank you for the reminder.
Good question. Thank you for that, Sheldon.
Yes, thank you. And thank you all for everyone for your questions. These were great. And certainly email me. Just if you type in my last name, make sure it goes to me and not David Kuligowski at Fisheries in Seattle. We do occasionally get each other's email. And one time I actually got a bill for a bunch of pH measurement material that was his. So Kuligowski alone will not get you all the way. I know. You would think we don't grow on trees, but apparently Kuligowskis do. So.
All right, thanks, Bob. And With no other questions here in the chat, we can start to wrap things up. I did want to say one thing and remind folks out there who have access to NWS, Slack, internal NWS and Slack. The Towers group does have a channel there, so please go ahead and look for that and join that. There's some great information being shared there. So with that said, I'll turn it over to Jordan Gert to wrap things up.
All right. Well, thank you so much, Bob, and thank you so much, Sean, and thank you to everyone here at the Minneapolis Forecast Office, the RFC, for hosting us the past 2 days. We've had some great discussions, and we'll be continuing that this afternoon. For all of you on the line, thank you for joining us. As is tradition, the book club does not compete with Turkey or NFL football, so we will be off next week, Thursday. Happy Thanksgiving, and thanks for you that have picked up a shift on Thanksgiving. But we will continue the book club on Thursday, November 30th, 2 weeks from now at 12 noon with Kevin Thiel, the SBC satellite liaison, discussing research to operations for the GLM. We'll leave it there today with, if you have any questions about upgrading your AWIPS to the next version of the TowerS RPM, Kashawn Bowman and Emily Maddox can help you with that, so please don't hesitate to get in touch with them. With that, appreciate everybody for being with us today and hope you'll join us again in 2 weeks. Thank you so much. Take care.